Hey guys, welcome back to another one. So here I'm going to be doing a complete walkthrough of the June 2017 C34, okay? And just like my previous ones, and at least my most recent videos, I'm going to, of course, have all the solutions out here ready and just literally guide you through every single step, okay? So, without further ado, let's go. Now, one, a curve C has the given equation, okay? So it's just a mixture of x and y's and set to 0. Find an equation for the tangent to C at the point 24, giving you answer in this type of form, where a, b, and c are integers. Now, what they want you here is firstly, a tangent to C is just a simple straight line equation, i.e. y equals mx plus c. Now, because it's a tangent to C, we just naturally need to find a specific gradient at the point 24. That's really it. And to get the gradient m, well, it's just a case of differentiating this and setting the values of 2, 4 into that derivative equation. Now, differentiating this is overall quite straightforward. You just have to do it term by term. So looking at the first one head on, we got 3x squared. Differentiating 3x squared, you can get 6x. Now for 2xy, I did on the right side, we need to use a product rule, guys. So you could do a head on, why not? But I always do product rule. So just let one of them be u. So I chose u as 2x and v as y. Differentiating both of these, you get 2, and with differentiating y, you get dy of dx. The reason why is because we need in terms of x. So this is probably dv. This is dv of dx. That's why it's dy of dx. Anyway, using the product rule, just multiply and sum them up. So we're going to have, and I always do it from the right, v times u prime, which will give us 2y, plus 2x, and dy dx gives us the term of it, 2x dy dx. And just keep differentiating the rest. When you do 2y squared, just drop the power 2 down, and you get 4y like you do for x. And because you're dealing with a y, times it by dy over dx to make it easy. And then finally, differentiating 4 gives you 0, and 0, well, 0. Now, here's the easy part. Now, all you have to do is literally collect the like terms. So collect the dy dx terms like this. Make dy dx a subject, throw it to the other side, and then plug in the values of 2 and 4. When you plug in the values 2 and 4, you should get 5 over 3, and this is the gradient, guys. So that is our m value. Now going back to the original equation here, we said the tangent C is y equals mx plus c. Now all you got to do is plug in the y over the 5 over 3 for the y equals mx plus c into the m slot. Now this is your equation thus far. And because we're working at the point 24, let's plug in the values of x equals 2 and y equals 4. And when you do that, you should get 4 equals 5 over 3 times 2, which is 10 over 3. And then plus c. And doing this, you can now solve for c, which is 2/3. So yeah, so this kind of method I think is very intuitive. It's very easy. You could use the standard y minus y1 equals m times x minus x1, or y equals mx plus c. I always use this. Now finally, when you have c equals 2 over 3, plug it in into the y equals mx plus c equation, and voila. And then put into the given form. So just times 3 across, subtract y to the other side, or 3y, and you have it. Done. So yeah, this is so far how the paper is going to be throughout. For the longer segmented questions, I'm going to do over at least a couple pages. So yeah, if you're enjoying this thus far, please give me a like, subscribe, share to your friends, and otherwise, let's move on. Okay, question 2, guys. So use integration by parts to find the exact value of the natural log of x over x squared from 1 to e, okay, with respect to x. Now straight off the bat, just to make your life easy, I'm going to rewrite x squared and put on the baseline, so it'll be x to the negative 2, so I'm going to bring it up, okay. Now in this case, because we're using by parts, we need to choose a suitable u. Now first things first, I'll tell you what you shouldn't do. You should never let the log x be v prime, the dv over dx. Reason why is because this is so hard to integrate, and it will make things worse. Now we always say this is u because when you have literally one rule of thumb is that when you have a natural log, always use e, always use it as u, and then let the other term be v prime or dv of dx. So that's what I did over here. And just a quick recap, the general formula to integrate by parts is uv minus the integral of u prime v, and you can just use it from here. So let's do this. So letting u equal the natural log x, differentiating this gives us 1 over x, and for v prime x negative 2, integrating this, drop the power, increase, add 1 to the power to minus 1, drop it down, so you get negative 1 times it will be negative x to the power minus 1, or minus 1 over x, up to you. Now using the formula uv, so timesing this term here, u with v, we get ln x times minus 1 over x can be written in this form. And then you just literally plug in the values of 1 to e, minus, and then using the u prime v, where u is 1 over x and v prime, v is minus 1 over x, plug it in, and then simplify this, you should get a positive 1 over x squared. And that's it, guys. This is just easy steps now. Now all you do is evaluate each segment. So evaluating the first half, if you plug in the e, you get ln e, which is 1, and this becomes e, so 1 over minus 1 over e, which is here. Plug in 1 to the equation, you get ln 1, which is 0, and that all cancels down to 0. And finally, minus 1 over e plus 0 is this. Doing the same for this one, integrating this term, 1 over x squared, very straightforward. You get the same result as you did over here, which is minus 1 over x. Plug in your e's and 1s, and eventually you should get minus 1 over e plus 1. Yeah, and that's it. Now you just add them up. So minus 1 over e plus minus 1 over e plus 1 should be over here. So I put it nicely on this side. And then sorting it out, make it look like this form, you get 1 minus 2 over e. Easy. Easy, guys. Yeah. Whew. So, so far so good, guys. If you're enjoying this, again, please give me a like if you haven't already. And yeah, just share this out with your friends. Anyway, let's move on to number 3. Okay. So it says here that the function g is defined by the following, okay, where we got the domains of x, which is all positive values. So this means x values can only be positive, i.e. the domain. Now, find the range of g. So the range of g is essentially what values g can take for a given x. So what I did here on the table, and what you should always do, if they give you like a certain limit or something, just start popping in values. I usually just start from, like powers of 10. So 0.1, 1, 10, 100, and so on. And I try to have an idea where these values can be. Usually, if you have like a simple like equation, you can graph it and just look at the equation and check out the height of it. Check out the y-axis, see how high the curve goes and where the limits are, if there is any limits. In this case, if you plug in the x values, you get g values of these. If you notice carefully, it seems to slow down towards 3. And since we already know one part of domain is greater than 0, we can see that the range for positive values of x will always give us at least the bare minimum positive value. So it's going to go all the way up to 3. So this essentially means that if you made x to, I don't know, infinity, or just made it really big, your gx will eventually go to 3. So we can say that gx lies between 0 and 3. It's 0 because we know it's positive. When you plug in a positive number, this is always positive. And we know if you put in a really big number, it will eventually cut off at 3. So the answer would be gx is between 0 and 3. Easy stuff, really. Okay, next one. So find the inverse function and state its domain. Well, I'll tell you right now, the domain of the inverse function is always the same as the range of the normal function. So if this is the range, then the domain would be between 0 and 3 for the inverse. Makes sense, they're inverted. Now, let's have a look. So to find the inverse function, I always do this nice formula. I always say, okay, let gy equal x. So I just rewrite this in terms of y, gy, and make equal to some x. Now replacing the gy, we're gonna have 6y over 2y plus 3, and now we just have to make y the subject. So just pretty much solve for y. So times this term across. So you're gonna have 6y equals 2xy plus 3x. Now what I would do for this term is to collect all the y terms on the left. So I subtracted 2xy across to get this expression here, factorize the y out to make it look something simple like this, and literally just slip it underneath. So you can have 3x over 6 minus 2x. And voila, this is pretty much the function we require, which is our inverse. Yeah, that's it, guys, all done. Now for part C, what do we have? So the function, find the function ggx. I love that. Writing answer as a single fraction in simplest form. Now what this implies is that we need to literally put gx, the second part, into the gx, into the g function. So this goes into itself. So essentially you replace the x here with gx. So the equation, so this x is going to be itself, 6x over 2x plus 3 for here and here. So it looks a bit like this, literally. It looks a bit like that. Now, to simplify this, well, it's just the algebra skills. I put a little tip here which literally says clear the fraction, guys. So my advice for these kind of questions, always multiply up and down by the lower part of the fraction, the smaller fraction. So since we got 2x plus 3, times up and down by 2x plus 3. If you do that, this cancels out, and you're just left with 6 times 6x, which is 36x. If you times this side, this bottom half by 2x plus 3, that cancels out, and you times this by 2x plus 3, you get an equation that looks a bit like this. 2 times 6x is 12x, 3 times 2x plus 3 is over here. And that's it, guys. Now you just tidy up. So expanding this and then collecting with the other with 12x, you should get 18x plus 9. And realizing that we can simplify this further by dividing 9, we finally get our result of 4x over 2x plus 1. Whew, not bad so far. Anyway, yeah, so if you guys again find this helpful, let me know. Otherwise, let's move on to number 4. Well, these questions are long, aren't they? Now function fx. What does it have here? So fx equals 27 over 3 minus 5x all squared. Okay. Now it wants us to find the series expansion of fx in ascending powers of x up to x cubed. Okay, this is a binomial expansion. Okay, that's what we're going to use, a binomial method. Now to do this, first thing, so we need to write it using this red form I put here, which is 1 plus ax power n. Now, unfortunately, this is underneath, so we need to raise it up. And to do it, since the power is 2, if we put it on the baseline, it would be a negative 2 powers, a bit like that. Now, another problem is that it's not in the 1 plus form, or at least this coefficient of 3 needs to be a 1. So what I did here is I factorized the 3 out. And when you factorize 3 out, you're essentially taking the negative power with it. So it'd be 3 to negative 2 out. Because if you did like a big bracket and took it out, you're going to distribute negative 2 to the inside and the outside. So that's why the power negative 2 is there. Now finally, now you just collect them together. So all of this becomes this term here. So take 3 out both, timesing it by 27, and it simplifies to 3 times all of these lot. Okay. So far so good. Now let's use the series expansion. Yeah. So if you guys aren't familiar, it's dead easy. Just make the equation look like this, and then this is the general form. It's always the power over the power over 1 factorial times ax, which is a in this case minus 5 over 3, plus the next term, which is n times, so power times 1 minus back over 2 factorial, and then so on. This is quite easy to follow. I mean, if you always make it look like this, it should be easy in exam. Now let's do it. So the very first term, we're going to have a 1. We're just going to use a 1 minus 5x over 3 part. The next term would be n, which is minus 2 over 1 factorial times ax, which is minus 5 over 3x. Easy. Plus, now the next term is going to be n times n minus 1, so minus 2 times minus 3 over 2 factorial, and so on. And then ax to the power 2, and then again, the next one would be similar. It will be n times n minus 1 and n minus 2. And all of that over 3 factorial. And we just multiply against ax, this time to the power 3, and so on. And it always goes up, so it'll be 3, then 4, and then you got 4 terms underneath, 3 factorial, 4 factorial. Really, it's very easy. Now, where are we? So yeah, now they want us to also simplify each coefficient, yeah? So literally, just bang this in the calculator. To do that properly, I would ignore the x. I would omit it from the calculator. So put minus 2 over 1 factorial times, in a bracket, minus 5 over 3. Doing this gives you 10 over 3. And then stick an x. Do the same here. Omit the x, put the square, omit the x, so everything without the x, including the square. You should get 25 over 3. Same thing, everything without the x, 527. And just stick the correct terms. And then multiply everything by 3, and voila. We should have 3 plus 10x plus 25 squared plus 500 over 9x cubed. Done. Not bad. Now, next one, part B. Yeah, so far good, guys. If you guys are following this, seriously, you're amazing. and really, I hope you guys do well. Now, so I'll put the answer over here just to keep it easy. So using the answer to part A, to find the series expansion in ascending powers of x up to and including the x term of this, let's go ahead and find the series expansion. Yeah. Okay. Let me think. Yeah. So what's happening here and here? So in the math scheme, they did it a bit differently. In the way I'm going to do it is that I'm just going to look at the two patterns and just see how does it compare to fx. Okay. So you got a plus 5x and this has a negative 5x. So essentially, it's the same function as fx, except now x is being reversed. It's pretty much the sign has changed. So you stick a negative x. So gx is really fx when it's negative. So f minus x. Now in terms of equation, if this is fx, you just replace x with negative x, so that means all the x's here have a negative x inside. I'm becoming kind of sick. So yeah, just expand it, guys. So 10 times minus x to give us this, minus x squared is positive, minus x cubed is negative, and so on. So it just alternates now. For the second question, notice how when you had 3 minus 5x, this is 3 minus x. This one has reduced by 5. So essentially, it's literally x over 5. It's hx the same as f when it's x over 5. It's just 5 times smaller. So again, like the previous one, replace the x in this equation here by x over 5 for everything. And then just literally open it up. Expand it and you should finally get this result here. Easy, seriously. Question 4 is quite straightforward. If you can spot this little patterns, then believe me, you're flying. Now, next one, number 5. Ooh, let's have a look. Alright, so A. Find the values of constants A, B, and C from this type of partial fractions. Okay, so this is super easy. Now, before I go ahead and tackle this, when you have something underneath like this, and then when you do partial fractions, always find the critical values of x. In other words, see when these equal 0, because we need to eventually eliminate them for later terms. For example, we can say 2 minus x will equal 0, therefore x equals 2. Do the same for the second term to get x equals negative half. So these are your key values we're going to use for later parts. Now, to solve this, the first thing you want to do is, or the second thing after this, is to multiply everything by 2 minus x and 1 plus 2x. If you do that, on the left hand side equation this disappears, so it looks a bit like that. And on the right hand side, a is going to get both of those two terms. B is going to cancel out 2 minus x and just keep 1 plus 2x. And C is going to cancel out 1 plus 2x and keep the other term, 2 minus x. Now, why do we do this? It's because once you test values, you can easily find the coefficients a, b, and c. So let's use our critical values, guys. Yeah. So when x equals 2, what happens? The left hand side, plugging in 2 will reduce to minus 20. On the right side, because if you pop in a 2 here, 2 minus 2 is 0. So the trick is to get everything to 0 except one term. So this becomes 0. When you plug in 2 here, you get 1 plus 2x, 1 plus 2 times 2, so you get 5 essentially. Put 2 here, this becomes 0. So you're left with minus 20 equals 5b. And solving that, you get b equals minus 4. Now, same thing, use the other critical value. When you use minus half, the left hand side becomes 7.5, or was it 15/2? If you put minus half here, this second term will become 0. So that cancels out, becomes 0. Put minus half, this becomes 0. So a and b are, these are literally vanished. Put minus half here, this becomes 2 plus half. And that's it. Now you just solve for c, because you have 7.5 equals c times, and this is 5/2. And then just dividing 5/2, you get c equals 3. Yeah, so partial fractions is very easy. Now, lastly, and this one is literally your choice, you can either do a couple things. You can equate coefficients, or you can just pick a random x value. I always pick 0 if it hasn't been chosen, because when something is 0, they just vanish. You don't need to do the math. So when x is 0, what happens? 5x becomes 0, this becomes 0, you're left with 6 on the left side. When you plug in zeros to x's here, you're left with just 2 and 1, so 2 times 1 is 2, so 2a. 0, you're left with 1, so 1 times b is just b. And you're left with 0, 2, so b c times 2 is c, 2c. Now, because we have the values for b and c already, you can plug them in. And when you plug them in, you can eventually solve for a. So now, plugging them in, we get 6 equals 2a here, minus 4 plus 6. And therefore, a is 2, guys. That's it. All done. Not bad. Not bad at all. Now, next two parts, b and c. So using part A, find the first derivative of x. Oof. Now this one is not so bad, kind of. So with these equations here, and I mean it, be careful. Try not to accidentally integrate these ones and make it a log, because I did that before, and trust me, that happens often. Try not to make this a log. Now, to differentiate this equation, firstly, rewrite this in the correct standard form. So it will be 2 minus 4 times, and raise this up. 2 minus x to negative 1. Same thing here, it will be 1 plus 2x to negative 1. So we want to keep it all in that standard format. Now, differentiating this, using the chain rule, that is, first things first, 2 becomes 0. Using the chain rule on minus 4 term, this term here, you drop the negative 1 down, so it'd be the same term minus 1, and then subtract the power by, drop the power first and then subtract it by 1, so it'd be minus 1 again. Actually, did I already say that? Sorry, I meant the differentiator inside will become negative 1, drop the power will become negative 1, and that goes down to negative 2. That makes more sense. So it'll be literally minus 4 times minus 1 and minus 1. For the second term, same thing applies. Drop the power and then differentiate inside, you get 2. Drop the power, you get minus 1, and then subtract the power by 1. That's it. And then just tidy this up now. So minus 4 times these two gives you minus 4. 3 times minus 1 and 2 gives us minus 6. And this is our final term. Done. And you can make it look like this as well. Okay, so C. Prove that fx is a decreasing function. Now, literally, a decreasing function is literally when you can prove that the derivative is less than 0. Likewise, if the equation asks for an increasing function, you just need to check if the first derivative is bigger than 0. Now, how do we do this without plugging actual values? Well, let's just look at the equation for a second head on. When you have a squared value, and this is usually popular squared questions, when you have a squared value, all of this becomes positive for every value x. And since we know x is always bigger than 2, when you increase the value x, without the square, this will be negative. When you're squaring it, it stays positive. Same thing here. When you square a value, it stays positive. So we're going to have basically minus 4 over a positive number, which by the way, keeps the sign, doesn't change the sign, it stays negative. Minus 6 over another positive number, again, doesn't change the sign. So you're going to have a negative number minus another negative number. And this means you're going to have another negative number. So this is going to be for sure less than 0. That's it. That's all you say. You proved it. If you can prove it's less than 0 and writing something like this, you're done. Okay. Well, so far so good. Let's move on to question 6 now. Okay, guys, number 6. Let's check it out. So the line L1 has the following vector equation. So you're given the position vector, the initial position vector, and the direction vector, which I call D1. And the second equation has the same idea but slightly different variables. So one is a scale factor mu, one's a lambda, and they all totally different lines. Now justify given reasons in each case whether the lines L1 and 2 parallel, intersect, or skew. Now intersect and skew is kind of on the same part. You just need to check if it intersects, then it's not skew. If it doesn't intersect, then we say it's skew. Now parallel is well, I'll show you how I exactly did everything here. So to prove something is parallel, we just look at the directional vectors, the ones I highlighted. We need to see if D1 is actually proportional to D2, or if there's some sort of scalar multiplier that can give you the same combination of results. Now doing that, I just said, okay, D1 proportional to D2. I plugged in the values and it's false because you cannot find a common factor. Like for the first one, you could say that 3 is half of 6. But 1 is not half of 3, and 2 is definitely not half minus 1. Because of that, well, it's not going to work, so the answer is not parallel. Now, for the next 2 points, intersecting and skew, we have to check one thing. To show that these two intersect, that just means that these two equal each other, the equations. And if they equal each other, it means we should be, and to prove that it intersects, we should get the same values for lambda and mu for every single combination equation we can make here. For example, we can rewrite this one as 5 plus lambda times 6, which is 5 plus 6 lambda. We can also write minus 2 plus 3 lambda, and so on. And also for the last one. Now to show that they intersect, or at least to have a go, we need to equate this one with this equation here, with the line 2 version. So again, we're going to have 10 plus 3 mu, so it's over here. And now we just have to literally take simultaneous equations. Now, to be safe, all you have to do is usually test 2 or 3. And what I do is that I take 2 equations. For example, I took the first and second equation. I solved them simultaneously, and when I did that, I doubled the second equation, and then subtracted the solve for mu, and then found lambda. And turns out I got mu equals 9 and lambda 16 over 3. Okay, seems okay. However, when I did another combination, I chose the first and the third pair. Turns out my mu and lambda were different, and because of that, we can say that different scalars implies skewed information or skewed lines. So they are not equal, so they are not intersecting. And that's it. That's all you have to do. Alright, now let's move on to 7, guys, yeah? Hey, so prove that this left hand side equals tan squared x. Okay, and this is a domain. Okay, alright. This one was a bit tricky, I'm not gonna lie, and I realized it was super easy. All you have to do is pick up that firstly we have a double angle, and secondly we have to show that the result that we don't have a fraction anymore. Okay, now one cool thing about this, and I usually do this often, is that I usually work backwards and as I move along. For example, I would convert, you have two options. You can firstly convert tan squared into sec squared form, or you can realize that tan is just sine over cos. And for some reason I felt that was more appropriate, because looking at the combinations of cos 2x, if you recall the double angle formula, cos 2x equals cos squared x minus sine squared x. However, using the sine squared plus cos squared equals 1 rule, you can rewrite the first equation as 2 cos squared minus 1, or 1 minus 2 sine squared x. Now, how to do this appropriately? Well, since we have a cos x and 2x, and one's minus, one's plus, you can kind of see that if you put 1 minus here or 1 plus, you can literally eliminate the 1's in both equations. And that's what I did. So replacing cos 2x with the third equation, and this cos 2x the second equation, I realized that the 1's cancel out and this becomes positive. I realized this one cancels with this one, becomes positive. And also the fact that sine over cos is tan. So yeah, that was my deduction, and this is literally I think what they're looking for. So that's literally a tip. Always try to work backwards and then see if you can find a meeting point in the center. Okay, next one, B. So hence or otherwise solve in degrees, by the way, so say calculate degree mode between 90 and minus 90 for this equation. Well, look at this equation again, it looks just like the first one, except this first one's been doubled, and of course they stuck in the theta. So what I did here is I factorized 2 out, so I got this term here, and realize now I've got tan squared x multiplied by 2, and there we go. So that's what I did. So now I just replaced all of this one with 2 tan squared x, and that looks a bit like this now. And I realized that thanks to some of the trig rules, you can rewrite tan squared x as sec squared theta minus 1 because of this property here. So just like sine squared plus cos squared is 1, you also have sec squared equals tan squared plus 1. Or the difference, sec squared minus tan squared is 1. So there's a couple ways to do that. So doing that, you just put sec squared subject, and now we solve in terms of sec. And trust me guys, this is easy. When you do in terms of sec, you can kind of just expand this times 2 across, tie this up and make it look like a quadratic equation, and voila, here we go. Now here's the ending. So now you got sec squared in a quadratic form. All you can use is a quadratic formula or factorize, like totally up to you. I use the formula because this one literally, you don't want to make a mistake, so you want to be safe. So doing this, I got minus half and 4 for sec theta. I convert sec theta to cos, so it's 1 over cos theta equals these two. And I just made cos theta subject, and I got these two combinations. Or I just do the reciprocals, really. You can take the reciprocals, it's fine. That's it. Now inversing the first one, well, you won't get a solution because cos only goes up between minus 1 and 1, so that's no solution, or mass error. And for the second one, inversing it gave me 75.5. Now to find, and oh yeah, realize that we're trying to find between this range, so we might have more than one answer. To check, I drew the cast diagram, and I always start from this corner. I always write CAST, so cast. And because we're working in cos, I'm going to use C for cos. I'm also going to use A because A represents all. It means it's always, if you have a positive result, you're always going to use A. If for some reason I was finding the inverse of a negative value, I wouldn't use C and A. I would use S and T because these only account for positive values for a specific trig function. Yeah. So that's it. Now you put theta there. So, and this is angle 0. So you just calculate from here to here, which was 75.5, and you just go down, which is negative 75.5. Simple. Very simple. Well. Just need to stretch myself a bit. So yeah, that's literally all we do. Now I think we're halfway. Let's move on to number 8. Okay, so 8. All right, let's do this thing. So trapezium rule. So figure 1 shows a sketch of a part of a curve. Okay, so I'm going to go straight to the example. So the table below shows corresponding values for x and y for the given function. Now use the trapezium rule with all the values of y in the table to find an estimate for the area of R, giving the answer 3 decimal places. Oh man, this is bad. How can I be yawning? Now to work this out, we just put the general trapezium rule. I mean, I wrote it a bit differently. I always write h over 2 times the first y value, which is here, plus the last y value, which is here, plus 2 times the rest of them, which is the highlighted area. Now h is literally, well, the height or the width of the bars. Because when we chop this up, we're trying to make many different trapeziums. So we can see that the difference in width between each one of the vertical height is 1. So it's like a sequence of ones. And yeah, so we just put h over 2, so it'll be 1 over 2 times, and the rest of the relevant values from the table. H first is going to be 0.6325, and y last is going to be 0.3742. Plug it in and you should get 2.377. Easy. Very easy stuff. Okay, next one. Let's see. Okay, so use calculus to find the exact volume of the solid of revolution form. Now write this in the simplest form. Okay, so one thing to note here, I added a bit to this diagram. The way to solve this very comfortably is to actually draw a sort of like a hollow circle to make it look kind of cylinderly, or at least draw some sort of circle. Now, just have, and that's literally what 360 degrees would be. So just to measure this, you can kind of see that the line from the center, which is the midpoint here, to the top would be the radius. And notice how the radius corresponds to the y-axis. So that's why the equation looks a bit like this. When we say the volume of R, you integrate from the 2 limits to 7, and we use pi, literally pi r squared, or pi y squared. So you can see that the radius dips as you integrate. So that's it. That's literally the theory behind it. Now all you do is integrate. Replace y with root x over x squared plus 1. Because you got y squared, you can just square this and keep the inside part. And now integrating this, I use substitution here, because with substitution method you can of course notice that when you have one term which is 1 power higher than the other term, you can differentiate this term to have an equation in terms of the 1 power less x. So example, 2x squared differentiate becomes 2x, and that has an x and this has x squared, so they can cancel each other. Anyway, let's have a go. So since we let u equal x squared plus 1, we can differentiate this, and then power drops becomes 2x, and then u becomes du over dx. Okay. My tip here for substitution is to always make an equation for u and an equation for dx, because you want to replace this dx as well with something in terms of du. Sorry for the yawning, guys. I think I've been sleeping quite late while making these videos. Yeah, I'm trying to pump as many as I can. So yeah. So in this case, I'm making dx the subject. We're gonna have du. So yeah, just times dx cross divide d2x, and you should get this. Done. Oh yeah, and the limits. Remember, these are x limits. So the whole point is you need to convert them to u limits. So we can say when x is 2, and we're using this equation here, u equals x squared plus 1. When x is 2, 2 squared plus 1 is 5. When x is 7, upper limit, 7 squared plus 1 is 50. Cool. Now we just rewrite the equation with the new information. So the volume of R is now pi times, instead of 2 to 7 for x, it will be u from 5 to 50. Now replacing, what is it? So we got x over x squared plus 1. Replacing x squared plus 1 with the variable u would be x over u. And now replacing dx, we're going to get du over 2x. And this is cool. So you can look at this carefully and you can realize you can cancel the 2's. You can also take the 2 outside interval because it's just a constant. So it'll be pi over 2 outside. And then you're going to integrate 1 over u. And thankfully, 1 over u is a common result. It's always the natural log. I think you're given this in a formula sheet. I'm not even sure. But you always get a natural log. Yeah, and yeah, it looks like we're done. Now you just plug in the values of 50 and 5, so it looks like this. Simplify this inside, so you're subtracting the logs, you have to divide the inside. So 50 over 5 is 10. Voila, easy. Okay guys, number 9. Ooh, vectors. Alright, I love this one. So let's have a look. So figure 2 shows a sketch of a triangle ABC. And given AB is given by some vector interpretation and AC is another one. Find the size of angle CAB. So CAB is from C to A to B. So I just labeled that X to make it easy. Now to find this one, it's just a general case of using the general cos formula, which is cos X, cos of the angle, which is equivalent to the two lines in between it, i.e. AB and AC. So we need to use the dot product between these two lines, so AB and AC, and then calculate its magnitude, AB magnitude and AC magnitude. So that's it. To find the dot product, that's easy. It's the second step here, which is AB.AC. So we literally rewrite these vectors ijk into the standard column form, which is 2, 3, -2, like this. And the second one as 5, -6, and +1. The k is just 1, so it'd be 5, -6, and 1. Now all you do is just multiply horizontally, as in 2 times 5 is 10, 3 times -6 is -18, and -2 times 1 is -2. And then you add them up, you collect them, and you get -10. That's it, that's your AB.AC. Very simple. Now for the magnitude, well, just use Pythagoras. So looking at the vectors AB, just square every single term, and then square root it. Literally, as simple as that. Second one, square every single term, 5 squared, 6 squared, and 1 squared, and square root it. So you get root 17 and root 62. Smash it all in, making sure your answer is in degree form, and then cos inverse, and you should get 107.94. Very explanatory, it's just very formula based. Always label what you're doing and it helps. Now let's move on to part B. Okay, so what do we have here? Now find the area of triangle ABC. Oh god, easy. Because now I just updated the diagram from the previous question. Because we obtained all the results, I update x with the correct angle and the correct lengths. Because magnitude is more or less the size of the vector, or in this case, the length. Now using area of a triangle, one way to memorize an area of a triangle is to always draw a separate triangle and call it the ABC triangle, where the angle C is between A and B. Now looking back at our triangle on the left here, we can see that we got an angle between two lengths. So using the half AB sine C rule, we can say half of A and B, which is root 62 and 17, times sine of the angle C will give us 15.44 units squared. That's it. You don't actually have to write units squared, but I usually do it just something I'm used to doing. You can write units as well to give it some sort of I don't know, some type of unit at least. Now let's look at part C. It's the shortest distance. So here's the values here, and let's have a look. So find the shortest distance from A to BC, giving you answers to 2 decimal places. Now when you have a shortest distance question, the first thing we need to think about is how do you make a short distance? Well, when you think of right angle triangles, the vertical length between them, where the right angle part, is always the shortest length. So we can think of it as the perpendicular length from some line BC to hit A. The perpendicular length is by far the shortest point, because if you did any other line, they would just be like layers of hypotenuses, and they will always be longer than this adjacent line. So always draw a straight perpendicular line from A to B, and let's call it P. Now, what do we have to do? So essentially we need to find the length of AP. Now to do this, there's a cool way to do this actually. I mean, it took me a while to think about this, but the way I presented this is that I'm just using the area of a triangle idea. So since we got a vertical height, we can say that, okay, we have a base here, we have a vertical height. So if you just twist the head a bit, a base here and a vertical height, and we can say that the area of this triangle, as we deduced, was 15.44. So base times height is 15.44, and of course half it, obviously. So we can say that our base is BC, we can say our height is AP, and we got area is 15.44. Now we just plug it all in. To find BC, because we probably haven't done that yet, you could use the cosine rule, or you could just be better than I do and just count to find the vector B to C. You just go from B to A and then A to C. We have B to A is just the negative of this, and A to C is the same. So if you're doing the negative of this, it would just be minus 2i plus 5i, which is 3i, minus 3j, minus 6j is minus 9j, and plus 2k plus k is 3k, and then you could find a magnitude of that. That'll give you an answer approximately equal to 9.95. Using the cosine rule is just my favorite. Just treat this the massive length as little a, and the corresponding angle here as 107.94. And call these two lengths root 17, root 62, and just smash away. I'm going to assume that you guys are well versed with the cosine rule, so I'll skip that. Now, yeah, just plug in all your known values, make AP the subject, and you got it. 3.10. Easy. Now, let's go and, let's move on to the next one, number 10. So, almost done, guys, almost done. Now, R-cos, R-sine, love this one. So I put a quick recap here. I put the general sine rule for two terms. Should look like this, plus minus, because that's what's required here. Now, A, write 2 sine theta minus cos theta in this form, r sine bracket theta minus alpha, where r and alpha are constants. And this is where alpha is between 0 and 90, and here we need to find the exact value r, and of course the value of t alpha to one decimal place. Now this is straightforward. What I do here is I equate these two, because since we're writing this in that form, that they're virtually identical. Now this is cool. Now for the right hand side, we just need to expand it using the general sine a plus b rule, part of the double angle or the expanded angle formulas. So you should get this in the C3 formula sheet, or I just memorize it because it's easier to memorize and useful. So expanding this one, so we get sine A cos B, so we get sine theta cos alpha, and because it's negative, it'll be a minus sign. And instead of cos A sine B, it'll be cos theta sine alpha. So always invert the letters, invert the trig signs. Now, we look at both sides and we say, okay, to solve this, we need to match coefficients. So I highlighted sine theta and cos theta for a reason, because I want us to match the coefficients on this and this side. We can say that in terms of sine theta, oh man, that was an ugly cough. In terms of sine theta, on the left hand side we have a 2, and for sine theta we have an r times cos alpha. So we say, okay, 2 must be identical to r cos alpha. And now in terms of cos theta, we have a coefficient of 1 here. Because they're both negative, we can ignore negative signs. We have a coefficient of 1 here, and we have sine theta times r. Because remember, r is you're going to multiply r to both. That means the left hand side, the coefficient of 1 is identical to r times sine alpha. And that's it. Now we have two pairs of equation. And yeah, we can now solve for r. So what I did, I just divide these two. Because one thing, the cool trick is that you can make a tan from sine and cos. If you divide sine and cos, you get tan. So dividing the two equations, so this on the top, the first one on the bottom, we should get r sine alpha of r cos alpha equals half. Tan, and then r's cancel out here, and then tan inverse, half, you get 26.6 degrees. And yep, it fits within the desirable range. Now, as for the alpha value, they want the exact value. So unfortunately, you can't just pop this alpha value in and solve for r. No. Actually, you can. If you have the exact answer, if you don't delete the answer in calculator, you could. But anyways, to be safe, I would use the right angle trig triangles. So let's just ignore this root 5 here for a second. Since we got r sine alpha is 1 and this is 2, if we look at tan alpha, actually more particularly, tan alpha is the same as opposite over adjacent. So this is your SOHCAHTOA. This is TOA, so opposite over adjacent. This means opposite, that the angle is 1 and adjacent is 2. Now using Pythagoras' theorem, you can deduce and get root 5, because 1 squared plus 2 squared is 5. Square root both of this will give you the length here, root 5. So therefore, using SOHCAHTOA again, to find the sine term is so it's SOH, so it's opposite over hypotenuse. So sine alpha equals opposite over hypotenuse, and cos is adjacent over hypotenuse, so we've got 2 over root 5. And that's it. Now plug this into, replace cos and sine or whatever you want, and voila, make r the subject and you got it, root 5. Yeah, maybe it's a bit long, but this is the form way. I mean, you could also just probably keep the answer here and plug in, see if you get the right answer. I haven't tested that, but I think it should work. Anyway, let's move on, yeah? B. Okay, so I put all the relevant info from the previous question here, just in case we need it. Okay, and of course I put a little cast diagram because it might be relevant for later. So figure 3 shows a sketch of the graph with equation y equals 2 sine theta minus cos theta. Here we go. Ignore the dotted line. Sketch the curve with this equation here. Now looking at it carefully, this is the same equation as the previous question here. Where is it? As 2 sine theta minus cos theta. And because we're writing in this form, we can also say that these two are identical. The only difference is now is that they have an absolute sign. So this means that this curve here has to be always positive for y, because whatever answer you get here, this will force it to give you a positive solution, so y would be positive, meaning you cannot have no negative trace. So that means these should bounce, they should reflect. So it looks a bit like that firstly. Okay, so that's the easy part. Now to find where it actually hits, well, thankfully we could just replace this equation with the arc sine theta minus alpha. Or we could just go use the fact that since we're shifting the curve by alpha, because remember sine just is like a regular, it cuts from 0, it's just a regular sine wave. This is shifted by alpha to the right, so it's like it started from this line 0, a bit like this shape, but then the whole curve moved to the right by alpha. So we can see it's moved by alpha, so by 26.6, and originally it's 180, it moves by alpha as well, 206.6. That's it. Now to see where it hits the y-axis as well, that's straightforward. All you do is realize that when something hits the y-axis, the x is usually 0. In our case, the theta is 0. So when theta is 0, plug in theta into any equation that we had. Oh, where did I put my equation? Damn. Oh yeah, put theta in this equation here. You're gonna get sine theta, sine 0, which is 0. Cos 0 is minus 1, so it's gonna be the magnitude of minus 1, which is plus 1, and that's why we get 1 there. Well, how did I forget that? Alright, let's move on to part C. So, here we go guys, almost done. Now, the temperature of a warehouse is modeled by this equation. Okay, so once again, the absolute value here. And now the only difference here in the previous one is that theta, it has now become 15t. So go ahead and copy the old R-sine equation, plug it in, because you can do that, and replace theta at 15t. So that's what we have thus far, okay? And I usually leave it in its original form, not the updated form. Now, blah blah blah. So state the maximum value of ft. Now, what this means is that we want to get the absolute highest possible of ft, and to do that, we need to look at every term. When we look at 5, the maximum value of 5 is 5 because you can't do nothing to it. Now, when we look at the bulk of this term, we need to see what we can maximize this to. What I would do is, again, plug in the R-sine equation, which I did over here. And now we ask ourselves, how do we maximize sine? Well, what we could do here is realize that sine takes values between -1 and 1, right? So we can say that the maximum value of sine is going to be 1. Because wherever you get the highest possible sine value will be 1. Because looking at this curve, well, that's not going to help you. You're going to get a 1. That's it. So that's for sure. So all of this is 1. And because you got r, you can take r outside, so it'll be r times 1, which is just r. So the maximum value of ft is 5 times r. 5 plus r. Or 5 plus root 5. Now, next part. State the largest value of t at which this maximum value occurs. And what this means is we have to differentiate now, because when you have a max and minimum problem, they're always talking about the turning point. So it's probably this turning point here or something. We need to find this maximum turning point here. Okay, so just go ahead and differentiate this. So where's the equation gone? So differentiating the equation here, well, 5 becomes nothing. Now, don't worry about the absolute sign. It just means that we're going to guarantee a positive solution. So differentiating this, using the usual sign rules, differentiate inside of 15t minus alpha in terms of t, and you should get 15. So that goes outside. You can take r outside as well because it's always positive. So it'll be 15r times the absolute value of the cos term. Okay. Now, in this case, and you have to make this equal to 0 because that's the only way to solve for t when you have derivatives and turning points. So make it equal to 0, and then realizing that if you divide 15r, that disappears, and you're left with this term here. Now you just do the easy steps. Now we cos inverse this to get 90 degrees, and realize that to get a maximum value, we can of course see the other values of t. Okay, so what I did, I just highlighted C and A because it's cos, and cos is C and A just means all for positive values. And since we know the angle is 90, we could put 90 there, and I just went around to 270 because 360 minus 90 is 270. And that's it. Since we got that done, this means that 15t minus alpha could be 90 or could also be 270. We want to maximize, so we want to use the 270 value. So we want a heavier upper bound value. That at least the top half needs to be heavier than the bottom half. And then just solve for t. Plus alpha cross divide by 15, put in a calculator, and voila, 19.8 is our max value. If you chose 90, you would have got a much smaller value. So don't do that, yeah? Anyway, that's it, guys. I mean, I hope that helped, and yeah, let me know what you think. These questions are a bit theoretical, so that's why there's a lot more explanations, and I didn't want to do it as I recorded. That would have taken too much time. I like to just quickly break it down and see how it goes. But as usual, if you guys enjoyed it, please give me a like and share with your friends. Otherwise, let's move on to the final parts. Okay. Oh, now this is thick. All right, number 11. So y equals 2x squared minus 3 times tan half x. Okay. Oof. I remember doing this. Find the exact value x when y is 0. Now, do what it says, pop in y is 0, so you have an equation like that, equate to 0. And now just make both of these equal to 0, because because the first term times the tan term will be 0. So essentially you have 2x squared minus 3 is 0, tan x over 2 is 0. Now, if you, for the first one, just make x subject, so plus 3 divided by 2 square root, you get root 6 over 2. To check if it's between the interval 0 and pi, well, it is, because root 6 over 2 is less than pi and more than 0, so that's fine, that checks out. And that was the only answer because it says exact value, so it's not plural. But to be sure, tan inverse the second equation, tan inverse of 0 is 0, times the 2 across you still get 0. But unfortunately 0 is not in the interval, since x is greater than 0, so we cross that out. So our only solution is the first. That's it. You also have a plus minus solution, but again, it's positive, so plus only. Anyway, moving on. Now, given that dy over dx is 0, given that dy dx is 0 when x equals a, show that this equation, the derivative, can be written like that. Okay, all right, let's have a look at this. Now, to do this, if we differentiate this one, we need to use a product rule because you have two different products. So that's why I let u equal the first part and v equal the tan term. Now, differentiating the first one is easy. Drop the power 2 and you get 2 times 2, which is 4x. 3 disappears. Now, for tan, it's a simple case of sec squared. I believe you're given this formula in the mark scheme. I think it's written as tan kx, so differentiate that and k goes outside. Otherwise, if you're not sure how to differentiate this, we need to convert to sine and cos and use the quotient rule to solve it. Anyway, this would give you this result if you did it. And remember, differentiate the inside, so x over 2 becomes half, which goes outside. And again, you rewrite the same term inside as always. Now, let's get back to the main part. So using the product rule, multiply v with u prime to get this term, 4x tan x over 2. Multiply u with v prime, and then tidying up a bit to get something that looks similar to this. So I just put 2x squared minus 3 over 2 and stuck in sec squared after it. Now, here comes the tricky part. So there's various ways to tackle this, but my tip is to always work in sines and cos. So convert tan into sine and cos, and convert sec squared to 1 over cos squared. Now, because it equals 0, fortunately you can just multiply cos squared across, so that cancels out, and this cancels out and you got one more term which goes in the top line, so it looks a bit like that. 4 alpha or 4x sine, it's the sine term and cos term. For the right side, this cancels out, so you just left with this term here equals 0. Now we have to ask ourselves, how do we get from this to the equation we want? Well, looking at this, the final result has a sine alpha, meaning the alpha 2 was removed. One thing you can also realize that this is actually the perfect expression for, at least most of it, for the double angle sine rule. So remember, if we recall that sine 2 theta is 2 sine theta cos theta, we can look at our equation and realize that the theta here is basically alpha over 2, which is what I did here. That means plugging this in or taking a portion of it. If you just take if you just separate the 4, if you half this value of 4, make 2 there and distribute it, you'll be left with 2 alpha, and this entire term becomes sine 2 times alpha over 2, which is just sine alpha. So all of this part with a 2 in front and isolating it will give us sine alpha. That's it. Yeah, and this is still the same. Now all you do is just simply, now you got this whole equation, just what do we do? Yeah, now you just times it by 2, that cancels out, that becomes a 4, and then rearrange it and it should look a bit like that. Easy. So that was the only tricky part, is to recognize the double angle property here. Next one. Now, oh yeah, this one is, oh my god, so easy. So now the iterative formula, which is given by here, can be used to find an approximation for alpha from the previous question, yeah? So see, by taking x1 equals 0.7, find the next two values, and remember to give it to 4dp. Now here's a cool trick here when you calculate, and you probably already know this because you're probably you're A-level math students. So what I would do is firstly put the value they want, put 0.7 in the calculator and press equal sign. Now your calculator is going to record this as an answer of 0.7. So what I want you to do now is to copy this expression as I did here and just write 3 over 2 times answer plus 4 sine bracket answer. This usually works, this works with Casio calculators, and I'm sure it works with like Texas and other brands. Anyway, what I want you to do here now is just press equal once and don't delete nothing. If you press it once, you get this value. If you press it again, equal sign, you can get this value. The reason why is because the previous answer is now the new answer. So if you're going to press equal again after this, you're going to get x4 and then x5. So yeah, you don't have to keep repeating it. You can just leave the answer button and just keep doing it. So yeah, definitely learn that trick. It's really, really helpful in exams. Now, that's done. So part D. By choosing a suitable interval, show that alpha equals this term, alpha equals 0.7283 to 4 dp. Okay, so what this means is that because we know it's been rounded to 4 decimal places, there must have been an upper and lower bound. So if you think of error intervals, it's always the same answer plus minus like an extra 5 at the end. So that's what I did over here. Test using alpha equals a term plus minus 0.00005. Because if you were to round these values, you'll get this answer here to 4 dp. I mean, this has to be just less than 5, but yeah. Now, all you got to do is really just call this the first alpha and second alpha. You just plug into the function equation, which, by the way, this function is from the previous question, yeah? We want to test if this value can give an answer above and below 0. That's the whole point of these questions, to see if this equation can give you an answer above or below 0 with our given values here. So for example, I plug in the first alpha value, this one, the 0.72825 into the equation here, and I get a negative answer like just below 0. I plug in the second one, I get an answer just above 0. So yeah, we can, and because of this, you give a conclusion. You could just say something simple like, hey, there's a change of sign. So what that means is that it crosses 0. So yeah, the answer must clearly be somewhere around here because it's so close to 0. So the answer is between these two. And that's it. That's all they want you to do. Nothing fancy. Very simple question. Just bounce. Okay. All right. So let's move on to the next bit. All right. Number 12. Oof. Differentiation. My enemy. So let's have a look. So again, I put so much detail on this page. So we're gonna go and discuss this step by step, how I came to this conclusion, and we're gonna quickly summarize this using some fast techniques. So figure 4 shows a right cylindrical water tank, so in the form of a cylinder. That's why I got the volume of cylinder over here just in case. The diameter of the circular cross section of the tank is 4 meters, so that's diameter, meaning the radius is half too. And it also has a vertical height of 2.25, the whole tank, whereas the water so far up to h after a certain time is h. Now water is flowing into the tank at a constant rate of 0.4 pi meters cubed per minute. Stop right there now. When they say this, it means that they want to find, this is a derivative equation. This is a change of rate. And a change of rate is always in the differential form. So I put over here, water flowing into the tank. This is literally the change in the volume meter cube over time. So dV, I call it 2 because there's 2 types. There's two things going on. dV over dt, which equals positive 0.4 pi. It's positive because it's entering the tank. There is a tap at point T, which is over here at the base of the tank. When the tap is open, water leaves the tank at a rate. So again, another derivative at this rate in meter cube per minute. So again, it's another dV over dt. So it's the first one I wrote here. Water leaves the tank. So this is, I call it dV1 over dt. And because it's negative here, it's because it's leaving the tank, hence the negative sign. So yeah, that's done. Where h is a height. Now, show that time t minutes after the tap has been opened that the height of the water in the tank satisfies the differential equation. We need to prove this equation. We need to formulate it. Now, a quick tip. We need to firstly count what variables we have. For these kind of questions, always check your variables. We know we have a volume V, because we're dealing with meter cube, so it's a volume, and we have a nice equation there. We also have h, which is the height. We also have time, because we always have time in change of rate, so that's always a given. So this means we can formulate an equation with all 3 differentials, with all 3 variables. Now, since we know one of them is dh or dt, I would write that down. And now I would write another term which which I don't know, you can make in any order, but you can write another term which you can kind of imagine cancels out of dt. Like just in a theoretical sense, if these were to cancel out, you'll be left with dh over dv. So that's why you can equal it like this. So you can make an equation which has dh over dt times dt over dv. These two cancel out to leave dh over dv. Now don't actually cancel out. The whole trick is that you need to substitute the values of this differential and this differential, and then just tidy up to make it look like that. Now for the volume, now just to take our time here, we have this derivative right here. It's just upside down from the first two versions. This is dv over dt, and same here. Because we have two, we always collect them. So you're going to add these up to make a total dv over dt of 0.4 pi plus or minus 0.2 pi root h. That would be the total dv dt. Because it's upside down, it'll be 1 over that. As for dh over dv, you need to work that out. So to work this out, we need to recognize the volume equation, which is volume equals pi r squared times height. It's pi r squared because you've got area of a circle, and it's height because there's some sort of height. So we're only interested in the water level, yeah. And realizing that the radius was 2, it's going to be 2 squared, so it'll make 4 pi. So 4 pi h. And then differentiating this in respect to h, so it'll be dv over dh. H disappears, you're left with 4 pi, and that's it. Now you plug in 4 pi here. And again, just like this one, this is upside down. So it's going to be, so dh over dv is the reciprocal of this. So it's 1 over 4 pi. So that's it. So we've got 1 over the sum of these two terms and 1 over 4 pi. So it should look a bit like this. Okay, so dh over dt times 1 over the sum of the rate of change equals 1 over 4 pi. Now all I did here is firstly cancel the pi's because, well, they're everywhere and you can cancel them out. And then I just times 4 across, and I times these lot across as well. So this term goes on the right hand side and 4 goes there. And then to prove this equation here, just times all of this by 5, because we know if you times 4 by 5 you get 20, and you just have to pray and hope to God that this will give you the same, and it does. And that's it. That's how you get the rate of change, the equation given. Bit tricky, but it's just a case of really try and break down as many steps and show some clear proof. Okay, anyway, let's move on to the next bit. Okay, so that's done. We complete A. So B. So at the instant when the tap is open, T is 0 and H is 0.16. Okay, so I put a little note here. What this means is that when time is 0, we get the initial H1 is 0.16. So that is from the beginning. However, after a certain time has passed, we get a height of 2.25. Well, actually, that's part B's reading. So use the differential equation to show that the time taken to fill the tank to a height of 2.25 is given by this. So yeah, the final time, after a certain time, this will be the final height. Now to solve this, you just have to solve this derivative. All I do in this one, my tip, is to firstly collect all the h terms together. So I treat this as one term, 2 minus root h. I divide all this to the left, so it becomes like this. And then I times dt to the right, or dt across, so dt moves to the right. And now we have it. I mean, for these kind of questions, you must always get the h terms together or the t terms together. If you don't have t terms, then, well, you can just stick a number term. But h terms must go with dh. And I just pop in an integral sign for both, and you're going to have, there we go, 20 over 2 minus root h dh. And now we just integrate. Well, actually, don't even integrate. You just have to make it show this form. And yeah, you just plug in the values of h1 and h2, which is a given. Done. And oh yeah, integrating dt, well, that's just 1 dt, so it just becomes t and plus c, and you're done. But we're not concerned, we just want this equation. Alright, so yeah, let's keep going. So now, using the substitution h equals 2 minus x all squared, or otherwise, find the time taken to fill the tank to a height of 2.25. In other words, evaluate. So let's have a look. So using substitution, I said let h equals 2 minus x all squared. Now differentiating this one is easy. dh over dx. Firstly draw the power 2 and then differentiate the inside and you get a minus 1. So it'll be minus 1 times 2 is negative 2. The power drops to 1, so it looks like that. Now, as always, yeah, for these kind of questions, you always want to find an expression that replaces dh. So make dh a subject for this one, times dx across, and you have something like that. That's perfect. And now you want to replace this h as well. So we already have it here. So for root h, well, you can just put a square root sign here and get rid of the power 2. And that's fine. Now, before we plug everything in, let's go ahead and change our limits. Because remember, these are h limits. We need x limits. So rewriting this one and making x a subject, square rooting it, and then putting x on the left and root h on the right, we should get x equals 2 negative root h. So we can say, okay, so when x is 0.16, h is 0.16, x is 1.6 in the calculator. So you plug it in, and when h is 2.25, you get another value for x. And yeah, let's put that in, and then we just update these values here with the x limits, and then substitute everything back in. So we're going to have 20 over 2 minus root h. Root h becomes 2 negative x, because remember, you just make root h a subject, guys. And yeah, dh becomes literally all of that, minus 2 times 2 minus x dx. Yeah, so now it looks kind of crazy, but it's really not, because you'll realize something in a sec. So let's look at this. Let's see what we can do to simplify this. With this 20 minus 2, if you multiply these together, you get minus 40, and it's a constant, so you can take it outside integral. That's why it's here. And then if you simplify the bottom, you have 2 minus 2 plus x, so that simplifies to just x, and you're just left with 2 minus x, so just put that on the top line. So it looks like this, and then you got dx. Easy. So that looks a lot more friendly now. Another cool thing is because since you just got a single term x, you can split this up as 2 fractions, and now you don't need to use a partial fraction method. It's just literally 2 over x minus x over x, which is 1. And that's it. Now you just integrate this. And just a tip, this one is definitely the log, and this one is definitely x. So integrating these two, and you should get 2 ln x, because 1 over x is ln x, and the integrating x is 1 is just, well, x. Then you just plug in the values, and we just say when x equals 0.5, you plug in 0.5 here first, minus, then you plug in 1.6, and those two should come to a value like this, minus 1.226, and so on. Then times that to minus 40, and you should get a time of roughly 49 minutes. Whew, intense. Not bad. Seriously, this paper is challenging. I admit, I spent some time to really try and make the steps easy. So yeah, let me know what you guys think. Anyway, let's move on to the last bit, guys. Oh, how many last bits are did I say? Okay, well, we have up to, let me see. How many questions are? Okay, question 14 I think is the final one. Yep, 14 is the last one. So we got 13 to go and 14. And here we go, guys, number 13. Let's check this out. Only 2 more to go, yeah? So, a colony of ants is being studied. Ooh, I love this one already. The number of ants in the colony is modeled by the equation, where P, I'm guessing, is a population and is followed by some exponential terms. Okay? So P is the number of ants measured in thousands. T is after the study started. Cool. So you can kind of see that at some point in time, the population of ants is dropped. Seriously, I think ants need their own like civil rights and stuff. This is totally unfair. Now, A, calculate the number of ants in the colony at the start of the study. Well, very easy. Start of study is over here, so it means when the time is 0. So plug in T is 0 into this equation, and just doing the maths carefully, you should get 190, so 190,000 ants. Okay, so 190 you'll get 190,000. Now next one, find dp over dt. So differentiate. So this is straightforward. So differentiating 200 is 0. Now differentiating this, well, you have a term on top of another term, 2 different functions. So this is the quotient rule. So just like the product rule, we're going to pick our u and v. Our u is going to be the top terms, and v is going to be the bottom half. So when you have that, you differentiate both terms. So let u equal the top half. And if you differentiate this, well, drop the power down. So it'll be 0.6 goes down, becomes 90. So 160 times 0.6 is 96. And you just copy it back. Same for here. Differentiating this time, so 15 vanishes, and then you will e to the 0.8t. So differentiating this, the power term, 0.8 drops. So you have 0.8 times e, and then copy it down. Easy stuff. And thanks to the quotient rule, the way it works is always going to be from v times u prime minus u times v prime, and then all of that over v squared. So this is easy. You just stick the 2 terms together. So this is quite self-explanatory. I, for some reason, simplified this one. I did 1/6 till 4. When you times these 2 terms, 160 and 0.8 gives you 128. Now e to the 0.6t times the other e term, because they have the same base, you just add the powers, which gave me 1.4t. And all over v squared, which is 15 plus e 0.8, which is all of that squared, literally. And then you can just expand the bracket and then collect like terms. You can get something like this, but I think this is sufficient as it is, minus the v squared bit. This is sufficient. Now, next question. Now, the population of ants initially decreases, all right? So we saw in the graph that initially decreases over here. So this is going to be literally the turning point. You can kind of guess that they probably want you to find the derivative. So using answer to part P, calculate the value of t to 2 decimal places. Now we have to set dp to dt to 0 because when you're differentiating, you're finding the rate change. So you're finding this is when the gradient is flat. At some point, the gradient is completely straight, so it's 0. So that's why the equation. That's why we use this formula. So when you differentiate this equation, wait, did I even do? Oh no, I already did. My bad. We already differentiated. We just set this equation to 0. Yeah. So when you set this one to 0, this is easy. You can just multiply the bottom half across, and that cancels out immediately. So that vanishes. And then you can plus 32 across, so you have something simplified to this. Now, this is just algebra. So what I did is I just divide 32 and I divide e to 0.6t across, and it looks like this. When you're dividing terms of the same basis but different powers, subtract the powers. So 1.4t minus 0.6t is 0.8t. This in the calculus is 45. And now you can just take the natural log on both sides. So that e cancels out, becomes 0.8t. And you have natural log of 45 and divide by 0.8, and you got your result. Straightforward. Very straightforward question. Now, here comes the big boss of the question. Oh, number 14. You're going to hate the integration. Actually, integration is quite easy. But you're going to hate the part C step or part B, whatever it was. Anyway, let's check this out. So, guys, let's have a look what we got here. So, figure 6 shows a sketch of the curve C with parametric equations here. Oof. Given that the point P lies on C, which is intersecting between the line and the curve, and has a parameter of theta equals pi over 3, so literally sub that in, find the coordinates of P. Alright, so this is actually easy. So since we know the parameter is this, plug in pi over 3 into x and y, and you get the coordinates actually. Plug it in and you get 1 and 4.5. And that's it, P is done. Next one, the line L is the normal to C at P. So normal is over here, so this means that it's perpendicular. It is a tangent equation, but it's perpendicular to it as well. So it's completely 90 degrees. Show that you can form this equation. Okay, so that's what the line equation is going to be. Now, we need to ask ourselves, to find an equation of line, as always, is y equals mx plus c. Now, first things first, we need to find what is the gradient at P. What is the m value? Remember, this m value is not the same m value as the normal. Once you find the gradient, we need to literally just find the reciprocal, the perpendicular gradient, which is easy to do. So first things first, let's find dy of dx as always. Now, we cannot find dy dx directly because we have thetas all about. So you could use the chain rule and just say, okay, if you got dy dx, I'm going to write dy here and dx here and smack out d thetas on both of them. So this means, firstly, find dy over d theta over here. And then as for d theta over dx, well, find dx over d theta first. Now, this is just a case of chain rule. To differentiate, to do dy over d theta, looking at the y equation, to differentiate this carefully, all you have to do is observe that this is, you got power 2. So I would firstly drop the power down. And think of it as inside the bracket. When you drop the power, you need to differentiate the inside the power, which is sine theta. Differentiating sine theta gives you cos theta. And now, because you draw the power 2, you got 6 times 2, which is 12, and then you leave the sine theta alone. So you have sine theta to power 1 times cos theta, essentially that, which is simply like that. As for dx over d theta, you drop the power 3 down, so you got 8 times 3 is 24. And now, and you reduce the power to 2, so you have cos squared, perfect. And now to differentiate cos theta, you get negative sine theta, so you write negative sine theta. So that's the steps. So quick recap, this is just a fast chain rule. Drop the power down, so it's going to be, for example, y would be 6 times 2 is 12, and keep the sine theta, so sine theta power 1. and then all you have to do is differentiate sine and get cos. Done. Okay. Wow. Anyway, let's move on. If you already know this, we can skip ahead. So I made a quick note as well. This is the chain rule steps right here, where you get y equals d6u squared. So we just let u equals sine theta, and we just differentiate both and then multiply the final two terms, and of course substitute u back in, you get that. Same thing applies here. Anyway, let's get to the next bit. We want to try and get this question solved. So once you obtain all of these, let's go back to dy dx. It's going to be the first term here. Because this is upside, this is reciprocated, you need to do 1 over itself to get d theta of dx times against dy d theta like we did over here. So it'll be this over this term, and you should get something like this exactly. Now all you do here is literally just cancel down as you go. So you got sine theta up and down, cancel them out. You got cos theta here and cos theta, so cancel one of them, or cancel both, and then you're left with one cos theta term. And then 12 and 24 becomes 2, 1 over 2. So literally it reduces to something simple. And now just remember where we are. This was the gradient we found at point P, but we want to find the perpendicular gradient. So it'll be this answer, you do the reciprocal and then change it to positive, and here we are, finally done. Now let's solve. Now let's plug everything back in. So using y equals mx plus c like I did, we're going to plug this back in, plug in theta pi over 3 because we need that, and plug in the points P to find the value of c. So doing all your things, putting the values in, you'll realize that when you put pi over 3 anyway over here, you should get a gradient of 1. So m is definitely 1. And then this is all 1, so 4.5 equals 1 plus c. Subtract 1, you get 3.5. Hence, we get the equation they asked for. Yeah, that's really it. That's literally it. Now, the final bits. Let's do this. I want to see if there's anything else. C and D. Okay. Right. So let's have a look. So the finite region S shown in figure 6 is bounded by the curve C. Okay, so we've seen this before. Show that the area S is given by two different terms. One which is an area of 4 and the second which is an area of 144 times the integral. Okay. Now, what I recommend for this question is that we should try and break into pieces. If I zoom in over here, let me see if I can. Okay, that's probably a bad idea. When I zoom in like this, you can kind of see that I split this into two shapes. At the point P, I always recommend this, but when you have an intersecting point, always draw a straight line down and realize that you can make some kind of triangle, rectangle, or in this case, trapezium. Now, to recognize this instantly, we can see that, just put this back here. Oops. We can see simply that the point P, as we found earlier, was 1 and 4.5, all the way back here. So let's label this height of 4.5 and x1. Now, to find this length here, this point here, we can see that this is when the line hits the y-axis. When it hits the y-axis, x is 0. So using the line equation, when x is 0, y is 3.5. So that's cool. So now we have pretty much an area bit. So this bit is covered. So technically the first area here is just simply the trapezium rule. We can use the trapezium rule, which is just the height of 3.5, the average of the two parallel lengths times the vertical height. So 3.5 plus 4.5, the average of that divided by 2 times the difference of 1. And that gives you the area of this trapezium. If it's a bit tricky, just use the area of a triangle method. So remember 3.5 plus 4.5 over 2 and then times the different length 1. Okay. Now here comes the main part. So now we need to find the area under the curve from P all the way up to this point I call W. Now to find what W is, now we need to go back to our parametric equations. So I'll pop them over here. These are the parametric equations from the early parts of the question, which was here. Okay, and we just have to see that when this curve hits the x-axis, and then y is 0. So I would use this equation here, y equals 6 sine squared theta, and find what theta is. So I can plug into the next equation and find x. So when y is 0, add w, I put over here. When y is 0, solving this one, theta is 0. And when theta is 0, plug into the x1. Cos theta is 1, by the way, so x simplifies to 8. So this means this coordinate here is 8. So we're going to be integrating from 1 to 8. And of course, the usual equation is y dx. The y equation dx. Now, what do we do next? So what we do now is we want to substitute a term for y and a term for dx. So it looks so it's all written in cos in theta form, and then update the limits of x into theta limits. So one step at a time, guys. Yeah. So for y, we have it ready. It's 6 sine squared theta, so we can plug in directly. For dx, well, we had it in an earlier question. We found where is it? Dx over d theta, which was over here, minus 24 sine theta cos squared theta. So so all you have to do is make dx a subject. So times d theta across, and we should get the expression right here, the highlight expression. So now we replace dx with all of that term that we just obtained. Okay, so far so good. And oh yeah, as for the limits, we can just have a look carefully. So when x is 1, we can say that theta is pi over 3, because we can use the again x equation here. Plug in 1, divide by 8, and then cube root and cos inverse, you get pi over 3. Plug in x is 8 here, and then solve, you get theta 0. So again, update the limits, yeah. Always do it properly as well. When you're changing 8 here, make sure you put 0 top. It looks weird now, but we're gonna fix it up later. Okay. All right. So back to the question. So to resolve this, now all you have to do is multiply this out. It just collect like terms, tidy up, and fix up. So we got 6 times minus 24 is minus 144, goes outside. Sine squared theta times sine, it gives you times cos, will give you sine cubed cos squared. So just stick the extra 2 on this, so it becomes sine cubed, and cos squared is still fine. All right, so that part is good. Now the problem here is that we want to get this long-winded expression. Okay, so it looks nothing like that, but indeed it actually is, because all you can really do is simply pick one of the terms and just expand it out. Notice how the sine theta is just sine theta, is like one, is a power of 1. So this is somehow reduced. So what I did over here, I just pulled out sine cubed to the right here and said, okay, let's write this in terms of sine theta and sine squared, because with sine squared, you can modify that as 1 minus cos squared. And if you do that, you're going to have 2 different terms. That's exactly what they want. So do it like that. And then plug this new term, sine theta 1 minus cos squared, into this equation. So replace sine cubed with this, and you got cos squared there. Multiply this out. So to make it easier, move cos squared in front. So you got sine theta cos squared theta times the entire bracket, and you should get the final expression here. As for the limits, if you just swap the limits, then you can flip the sign, because this will give you like a negative. This will give you the same answer entirely. If you do a small limit minus a bigger limit, you'll get the same answer but a negative version of it. You get a negative answer. Big minus small, you get positive. So that's why we flip the signs too. And yeah, that's it, guys. That's literally partially done. Now let's move on to the final part of this. Okay, so I call this one S, just because that's what they call themselves, the area of S. Now, hence by integration, find the exact area of S. Okay. So for this kind of form, since you've got 2 different parts to integrate, which you can combine, by the way, but in this case we won't. I would call the first term R1, second term R2. So we're going to integrate. So let R1 be the integral from 0 to pi over 3 of the first term, d theta, and R2 be the second term. So we're going to do step by step, yep. And when you do it, you can kind of see that, of course, since we replace the integrals, this will be the final form of the answer, R1 minus R2. It's not the only way, it's just something I prefer. So now integrating the first term, the first integral, it's dead easy. When you look at this head on, you got to ask yourself, pass or substitution. The rule of thumb is to always use substitution first. And when you have sine and cos, the tip is to always use u on the bigger power term. Not all of it, just like parts of it. Because if you differentiate, you're going to get a term, a trig form in the same terms of its opposite. And then you can entirely solve it. So always use it, for example, the basic one, like cos theta. So I said let u equals cos theta. Differentiating this gives us negative sine theta. And now all I want to do is make d theta the subject here. So d theta, just times d theta across and divide minus sine theta. You get something like that. Okay. And likewise, the limits, again, you have to update the limits into u limits, because we're working in u's now. So you can say when x is 0, or when theta is 0, plug in theta is 0 into the u equal cos theta equation, so you get u equals 1. When theta is pi over 3, plug it in, you get half. U is half. That's it. So update the limits. And now just go ahead and update everything you know. So going back to this equation, limits are updated. Sine theta, there's no sine theta expression. There is, but we'll get to that. For cos squared theta, replace that with u, so it'll be u squared. D theta, replace it with d over minus sine theta. Now, this is done. So now, as you can probably see, the sine thetas here cancel each other out. You can take out the negative sign, so, and that's it. Now you have minus the integral from 1 to half of u squared. And that's just u3 over 3. That's just add power 1, divide by itself. Evaluate this, and voila, 7 over 24. For the second integral, it's the same thing, but now you have a power over 4. So you don't have to do these long steps. So it's the same method, except you have a power over 4 instead. Everything's the same. So this becomes u5 over 5, and that all simplifies to 31 over 160. So now with our given values of R1 and R2, we can finally plug into the original equation here, and done. You should get 18.1. Oh, that's it. Anyway, guys, thank you for watching. That's been, for me, it's been one hell of a ride. It was a long question, and yeah, intense. And today, as of my recording, today is Eid, so we're going to be enjoying that today. And I hope you guys are all having a lovely day. If you enjoyed my videos, please give me a like. I admit this was a bit more challenging than recording other questions, because there's a crazy number of steps, and I can imagine it gets tiring to listen to all of them. So I try to make it as engaging and, you know, not too dull as possible. But yeah, let me know what you guys think. Give me some feedback, and yeah, I'll catch you guys next time. Ciao.